All right, so we have been talking about why we have cache misses. And in the last lecture, we talked about hardware optimizations to address those cache misses. But as you can hear, all the hardware optimizations come with a cost. And the success of a company or a business or a solution typically should not just rely on hardware optimizations. And in fact, whenever there is an additional cost, people will not be willing to accept it, right? And a lot of business, they need to be profitable to survive, right? So that's why a lot of you probably already heard about like DeepSeek these days, right? And why it has such a huge influence, because if what they claim is true, right, that would change the game, right? Because someone finally figured out how to make supporting this AI service more affordable. But without knowing too much detail, it's hard to tell at this point because it's a little bit beyond our imagination. But let's set it aside. It also tells, but the thing is that it changed all the stock market these days, right? So the thing is that one thing you have to really pay attention to, right? Like those companies, what they care is not about how fancy is the feature, it's more about if this thing is profitable or not. So, and how to make it profitable is, given what you have, can you maximize it, right? So that's why we want to talk about the software version. But where we are coming from? We are coming from the fact that we are living in a world where your processor and memory, although they are both important, in fact, they are equally important in volume architecture. However, one is a lot slower than the other. So the slower side is the memory. So as you can see from this plot, the purple line, the purple dotted line, express the ratio between the latency of your processor and your DRAM. And it shows a 55 times slower performance given the modern technology. To mitigate that, we have built a hierarchical memory. However, there is no perfect solution. There is no perfect memory hierarchy. There is no perfect cache organization. So sometimes if you have a code like this, then turns out that, well, from the software perspective, it works really well. However, it's a disaster in terms of cache performance, right? So, sometimes you were thinking about, okay, how can we organize our cache to mitigate that? There is always a cost with that. So for example, if you want your cache size to be larger, the access time itself would be longer. So it means that you are slowing down every access, no matter it's a hit or miss. Or if you want to have more weight associativity, it will also make your power consumption higher as well as your access time even longer, right? So both are less ideal, suboptimal. And like one of the mechanisms people talk about is prefetching. However, prefetching also comes with the cost that you are going to kick out something that you really want, right? So for example, a lot of people, okay, you guys want to know something after the midterm, you want to learn a lot of stuff after the midterm, right? But sometimes if you try to know too many things before taking that test, then you are probably going to forget the most important thing when you prepare the midterm, right? So that's why a lot of cases I'm a little bit like hesitate about like telling you the whole answer, a complete answer, just give you a short answer because of that, right? Because I don't want you to mess up your learning at this moment, right? So another idea to remedy this issue of prefetching is stream buffer, which we put the prefetch block inside the stream buffer, right? And another issue is actually the conflict miss in the NVIDIA processor, right? But a solution that would be really useful is actually victim cache. So whenever you have a block being kicked out, you just give it a temporary storage. So the next time when you want to revisit it, instead of going to L2, you can find it there, right? So that's where we are. However, again, all sorts of hardware solution, you will need some kind of hardware, which means that you need additional circuit, you need additional area, which costs more money. So today, we're just going to talk about one thing, how can we optimize the code performance without adding any new hardware? So that's what's really important to you as a software programmer. So first of all, we talk about data structures. So take a look at these two data structures. And assuming you are performing a SQL query like this, which one would give you better performance? All right. Why don't you guys go ahead and discuss with others, right? I would expect that's the answer, right? So why don't you guys go ahead and discuss with others? All right, let's take a look. What do you guys have? Oh, okay. So amazing. Okay, so before I run a demo, I want to hear from your thoughts why a lot of you shifted from this side to that side. Anyone would like to share? If you are hesitant about saying, oh, this is what I saw, you can say, my friends, right? After our discussion, this is our decision and this is why. Right? So it's not you, it's not about you, it's about your group. Would that make you feel better? Alvin, are we friends? Okay, what do you think?
Well, my group said that for A,
Uh-huh.
an array of objects,
Uh-huh.
and there's an array of students.
Uh-huh.
Each student has an assignment 1, 2, and 3.
Mm-hmm.
But for the second option, it's grouped by each assignment,
Mm-hmm.
and each assignment has a field of students.
Mm-hmm.
And so we said, since we're trying to calculate the average of one assignment,
Mm-hmm.
it's better to access one assignment within a block.
Within a block, or so we have to organize this better, right? So okay, so let me guess. This is what you are probably going to say. Okay, so one thing that you really have to practice in the future, right, for your midterm or your final or even your assignments, right? A lot of cases. Okay, so I read your comments. A lot of you blame what we have issue is actually the formatting, but to be honest, it's not about formatting. Some of you didn't get the credits because you never explained how do you get those numbers. So none of the question in this class would just ask you for the answer. We always want an explanation. We always want a justification, right? So all I want to see is the justification. That actually matters. And sometimes a lot of people, they give me the answer and I need to guess, right? And when they come to me, ask for regrading, they say, hey, you like, based on what I put here, you can probably know this is what I want to say. Yeah, I probably can know, but I can also interpret it in a different way, right? So you really need to be really specific regarding how to organize it well. So this is what we would do, right? So if you have a data structure like this, and this is actually the data structure that after you take some kind of object-oriented programming class, they would suggest, right? All the teachers teaching that class tell you, you should do this. But this is actually not that ideal for performance, especially for our case. Because if you think about that, right, basically what it does is that it would allocate consecutive memory space for assignments from the same students, right? So what we end up with is that here is your memory layout. You start with a student ID, a few assignments. The next student's ID and a few students, right? So what will happen if I just want to count the average of assignment 1, which a lot of cases in database queries we want to do that. Then what will happen is that I will grab a block, cache block, that is pretty large, but in fact, I'm only using one of the elements. And then I don't use the whole block. And I have to go to another block. Again, I'm only going to use this one element. And every time you visit that block, it's likely a miss, no matter it's compulsory miss or capacity miss, because for a large database, you have to fetch so many records, right? Thinking about like UCR, we have more than 30,000 students. So we would definitely saturate the cache capacity if we want to do such a query for everyone's something, right? So this is not ideal. However, if you are able to declare your data structure in this way, which is less ideal from the perspective from the object-oriented programming. What it does is that, okay, I treated the whole database table as a giant object. And within this object, I have a few pointers. Each pointer is a consecutive array that stores my column data in a table, right? So it turns out if I want to take the column average, everything is consecutive. So you can better exploit the spatial locality, right? So the spatial locality is actually the keyword that I'm looking for, right? When you answer your assignment, sometimes you think, okay, I have done my explanation, but as long as I didn't hear that kind of keyword like spatial locality, I'm not going to give you any credits. The same thing for midterm, the same thing for final, right? So sometimes when you answer those questions, send it through the auto grader, you didn't get a grade, you blame the script that I wrote. But actually the script is simplifying what I would do when I'm grading, right? And in fact, we have done stats. With auto grader, everyone's assignment score is higher than human grader, than our TAs, right? Once I show that, people feel like, okay, we will go with auto grader. We don't want a grader or TA anymore, right? But to be honest, what we're really looking for is that kind of specific explanation. Same thing when you are doing your job interview. We are hiring experts. We are hiring solid engineers. If you cannot express your idea in a very elegant way that shows your knowledge, because a lot of cases I hear people answer when they are doing interviews or answering midterm, I already feel like this is not the person we want to hire, because a lot of cases people just throw a lot of stuff they think that is relevant to the question that our answer that the interviewer is asking. But that's not the right strategy. In fact, if you do that, if I'm the interviewer, I immediately know this person doesn't even know what I'm asking. So I would definitely not hire that person. So learning how to answer a question to the point is actually the soft skill that you should try to develop from this class, right? So for this specific question, if you just want one-line explanation, what you want is that version B can help us exploit the spatial locality by allocating the same assignment in consecutive memory space. But the other one, there is always very low utilization of data within a block, cause more compulsory or capacity misses, right? So that's the short version of the answer, right? Okay, so, but how significant is that in performance? So let me run a demo. Okay. Oops. Okay, so let's do this. So this is the data structure we have. Wait, not this one. Okay. Okay, so this is the code that we have, right? The left-hand side is exactly the left-hand side you see, except that the homework become assignment, right? And here, the right-hand side is also corresponding to what we have, but right now we only have one assignment, right? So that's what we are. And we assume we have around 30K students, and we assume we have like 10,000 homework items for students to take, right? So that's what we have. And this is the code. And we want to take the average, right? So that's the code that we are having. So yeah, and this is the loop that performs the counting of the average, right? So now let's run it, and let's run it from scratch so you can see exactly the difference in number. So it takes a while to run because it's quite a lot of, so if you have an array of objects, which is the version that your object-oriented programming teacher would teach you, it would take 8.5 seconds. But if you listen to your architecture professor like me, you will save the money like 50% of the cost or even more by running it at 3.5. And your user will feel a lot better, more responsive of your service if you do it right. Right? And in fact, most of the database systems, we use column store instead of the row store. So a lot of you, when we are thinking about database system, we always thinking about the table that we would see in real life, right? And if you look at the table that we would see in real life or what they presented to you through some of the SQL management interface. This is typically the table they would dump for you, right? So if, for example, if here I have 5 different columns, then this is you think it looks like. And a lot of us would think they would do row store in a way that we will start with the first row and the second row, the third row, the fourth row, and the sixth row. But the answer is no, because if you think about most of the database queries that we are doing, right, it's pretty much like this, right? Select, right? Select is probably the most intensively used SQL operation, right? And whenever you select, what are you selecting? You're selecting columns, boy, girls, whoever, right? So you are selecting columns from the table, right? You're not selecting a row. You're selecting the whole column instead of a whole row, right? Well, you would have some where closure to give you some conditions, but still, when you are picking, it's based on columns, not the rows. So turns out the real storage is based on column store. Most of the database nowadays, they use column store instead of a row store. So what does that mean by column store is that this is how we store data. We have the value, we have an index, right? And then the next value, next index. Same here, the value, index, until we finish a column. I know some of you might have the question, like, oh, okay, it sounds like if I want to insert, there's a lot of cost. But here's the thing. When we design stuff, there's always nothing perfect. There's nothing perfect. So we have to think about what's the more common cases. So in database system design, the chances where you are going to alter is relatively lower than the chances where you are going to query. So you have tons more reads than writes. So when we design column store, it also means that we are somewhat optimized for reads instead of writes. Because the fact that most of the time you are just querying the database without altering it. So of course you can use row store, but that's only if you have the strong cases to argue that, okay, I'm always going to manipulate each people instead of the relationship among them. Okay, so that goes to the first part, right? The first thing to optimize in your software is that, can we carefully rethink the layout of our data? And if you could have changed the layout of your data, you can reduce the amount of blocks that you need to fetch because you have better spatial locality. You have higher utilization of data within the same block, right? So you can reduce the capacity miss, and as long as you have fewer blocks, there are also lower chances to hit conflict misses as well as compulsory misses. So it's good for everything. So the fundamental of software optimization in cache performance is actually choose the right data structure. Choose the right way of implementing your data structure, right? So that's the first thing. Okay, the second part, we are going to talk about how to write a loop. So you might think, are you kidding me? How to write a loop? Such a simple thing, right? But there are actually a lot of things to talk about in writing a loop. So we already seen this example, right? Like depending on the index you have, right, the CPI would be a lot different, right? So I don't think we need to explain that too much this time. But this mechanism is called loop interchange. So loop interchange means that I am changing the traversal order to ensure the traversal order would in favor of our data layout in the memory so that we can exploit spatial locality. So that's loop interchange. So right now, how about this? How about this, right? For this one, there's no other loop for us to interchange, right? So it doesn't help. So for this kind of loop, how should we optimize it? How should we optimize it? So I provide a different version. Can you help me evaluate if this is a good way of writing the loop? All right, let's take a look. Okay, I love this. So it means that we need discussion. So why don't you guys go ahead and discuss with your friends? All right, let's take a look. Okay, after discussion, 74% of you think it's A. So I want to hear from you. Why is it A? Versus only around 10%. Anyone would like to share?
Just for the first loop,
Mm-hmm.
you have 4 arrays,
You have 4 arrays.
and then you have AK elements.
You have AK elements.
So the miss rate for that will be 1 over 8 because you have enough. It's called associativity.
Okay, so this part we have 1 over 8 miss rate, because what kind of miss are we seeing here? Compulsory miss, right? Why don't we see those conflict misses? Right, so here's the thing, when you answer this kind of question, right, you have to tell me what kind of misses are gone, what kind of misses are remain, how many misses are compulsory misses, right? And that's a good answer, right? So 1 over 8, that's a chance. How about the second one?
So the second one, you have 2 arrays.
Yeah, I have 2 arrays.
And the miss rate for that one would still be 1 over 8.
Okay, why?
You have 1 miss per 8 elements for both.
For both? For both?
Are you saying if there's reuse from the previous loop for EI?
What do you think?
I'd have to see.
You have to see.
If the cache is filled.
Okay.
Previous loop. Yes, if you have 4 arrays, 32. Yeah, the first loop, the whole cache is full, because you have.
How do you know?
Because you have 4 arrays. Each of them are 8 bytes.
Mm-hmm.
And you're doing AK iterations.
Mm-hmm.
So should be 4 times 8, 192 times.
Is it 4?
Oh. Eight bytes times.
So each element is 8 byte, right? And I have 8K elements to traverse, right? So that's actually 64K. So you are anyway going to see a capacity miss. Even I want to keep all the E's, right? So that's the case where we are going to see capacity misses. And previously, we don't see capacity misses because we never reuse the EI. But this time, we have to reuse the EI, right? So based on that, right, actually A is the right estimation because we are going to see this miss rate anyway. However, right now, we have 2 types of miss in play. One is compulsory misses. However, the EI here, it becomes capacity miss. Because we already have the EI before. And the reason we cannot keep it is simply because if we want to keep the whole EI, you will need 64K. And given you have a 32K cache, there's no way we will keep it. Makes sense? Right? So the answer is actually A. And we can also run a demo to see if that works. So here's the code. And this mechanism is called loop fission, which we try to split a loop into two. So again, I have this two version of the loop. And what I'm going to do is that I'm going to run the code with and without. Okay, so what I'm going to do is that I'm just going to show you there are difference in cache misses, right? So if you check, this is the version A, right? You will have a miss rate of 1.7%. However, you should remember this 1.7% is also including the initialization phase, which does not in a loop. And the last time we subtract that part, it's actually 100%, right? But now for the newer version, it's only 0.7%, right? So all the misses that belongs to the conflict misses are gone, right? So that's why this optimization works for that, right? And with this software optimization, you don't really need a victim cache anymore, right? So most of the architecture right now, they don't have the victim cache. Instead, we encourage the programmer to revisit their code, right? If they know exactly the architecture they are running, right? So if you have a processor like NVIDIA, Tegra X1, like if you are writing a game for Nintendo, which use NVIDIA Tegra X1, you should think about, okay, when I performing some calculation, I should never consider concurrently visiting 4 data structures at the same time. More than 4 data structures at the same time, otherwise the performance would be bad, right? Okay, this is called loop fission, where we try to split a loop into two. So the loop fission is actually a pretty good approach to help us mitigate the conflict miss. Now, how about the code we run? For this code, if we run it on Intel processor, how does that go? All right, let's take a look. Okay, it looks like we got D as the most popular answer, but there are also about half doesn't agree with it. So why don't you guys go ahead and talk to your friends?
So
Oh, I think this is not setting correctly. Okay, so I think the option, okay, here we go. So again, it's D. So, well, before we run a demo, why is it D? Okay.
We could discuss it at how like there's multiple ways.
Uh-huh.
So we were able to allocate all those 5 variables. Comparatively to the one before, we only had 4. But now since there's 8, there won't be like issues about cache misses. So
So, well, is there no cache misses or?
well, there's fewer cache misses in this case.
What do you mean by fewer?
Kind of since there's more ways,
There's only compulsory misses,
Okay.
right? There's only compulsory misses, right? There's no conflict misses, right? And if you look at the code that we have on the right-hand side, so another way of saying this, right? After your analysis, both sides, they would have like a 1/8 miss rate. However, if you check the number of memory operations that we have to perform, here we have to access 4 in this loop. And here we have to access another 2. So it's a total of 6 times AK. But here is only 5 times AK, right? So if the miss rate is about the same, you can pretty much imagine the CPI of access memory is about the same, right? So if CPI is about the same, what matters? Instruction count, right? So left-hand side apparently has more instruction count, right? And the instruction count is contributed to the increase in memory references. So that's why the answer is D, right? However, right, what does that tell you is that, okay, loop fusion, if you're working on a processor like Intel, the loop you should write is actually this version. Question?
Does that mean like there's libraries and code that allow you to like check the processor that the user is running?
I mean, you have to, well, that's a very good question. The library itself has to implement that check. And to implement that check, you have to run some low-level assembly language with the architecture built in, like the database of the architecture built in. So, for example, if sometimes you see some sort of code, it won't run on newer processors, or it won't run on some processors, that typically means they have optimizations like that, right? So what does that also mean is that it's not an encouraged practice in implementing software, because the processor technology changes every year. And they change the CPU ID all the time. So even though you check the CPU ID, if it's not something that you have known, you still have to modify your code, right? So what you mentioned works for if I design the library specifically for a vendor. So for example, like Intel, they have their own Intel MKL library for linear algebra. And MKL only works well on Intel processors because they only optimize for Intel processors. AMD has their own version of BLAS library. But again, that's only optimized for AMD version, AMD processors. So that's what you have to do end up with, right? You have to write your code to optimize for the target platform you have. You can write multi-versions of the code, but again, there's no guarantee you can switch to different mode correctly. So most of the in production ones, they don't do that, right? But what does that mean is that as a software programmer, you saw the software engineering is telling us not to be worried about your underlying architecture. That's only true if you really don't care about the performance, you really don't care about the cost. But if you really care about the cost, you have to figure out what's the right way of doing it. And as you can tell, if I'm the compiler, what am I going to do? No, I'm not going to do anything for the loop that you wrote. If you wrote your loop in this way, I'm not going to optimize it. If you wrote your loop in this way, I'm not going to optimize it. Why? Because I don't know if doing this is better or worse. You can pass the hint to the compiler. Like there is a microarchitecture flag that you can specify specific type of CPU you want to optimize the code for. If that's the case, the compiler can potentially change your loop based on that specific architecture. But otherwise, if you don't pass that specifically mark flags, compiler is not going to do anything. So that's why you, as a software programmer, you have to know that. Right? So the takeaway is loop fusion is better to address the capacity misses, right? Because we mentioned previously, when we do this loop fusion, when we revisit the E array, we actually have capacity misses. But if you do loop fusion, they are gone, right? So each of this, they are addressing different type of misses. If you have problem with conflict misses, you should do fission. If you have problem with capacity misses, you are probably going to deal with that, right? So those are that. Okay, let's talk a little bit about probably the most global problem nowadays, matrix multiplication. But before we talk about matrix multiplication, which is the most essential operation for machine learning training process, we should talk about what really a matrix looks like in programming language. So the memory space that we have is only one dimensional, which means that everything is linear. So if you have a matrix, it has to be mapped to this linear space. And this is how we map. We typically map it by a row order. What does that mean is that for each row from the matrix, they would occupy the consecutive space. And the initialization of a 2D array is essentially like this. First of all, you create a two-dimensional pointer. And this 2D pointer is, the first dimension is essentially an array of pointers. And each pointer is actually pointing to another array where you store your real data. And those real data, they are stored consecutively. So what does that mean is that the first level of this two level is just pointers to array. And the real array, so this is the first level, saying that I have 4 rows. Then you would have 4 in the first dimension. And each this like A0 is actually a pointer to this location, which is an array led by A0. And for A1, it's also a pointer to part of the space. And sometimes if you're lucky, most of the time, if you're lucky, if you initialize this consecutively, the malloc library will typically give you consecutive space. But sometimes if you're really unlucky, or your malloc library is performing some randomization in your address space, different rows, they might not even be consecutive. Okay? So that's the concept, right? So you can, but assume that you're lucky enough, right? You can think the most trivial way of mapping from 2 dimension to 1 dimension is AI of j is essentially AI times plus j. Okay? So here's the matrix multiplication, right? Here's the most naive code that you will write. 3-level nested for loop. And Cij would be equal to, plus equal to Aij multiply Bkj. So we are taking a row vector and multiply with a column vector. The dot product would be the result, right? So that's where we are. What's the algorithm complexity? Over n cubic, right? So based on that, from what you have learned so far, right? If I set for 1K by 1K by 1K, it takes about 2 seconds. How much you would imagine for 2K by 2K by 2K? How much time? 8 seconds? 16 seconds, right? 8 times, right? Okay, so let's run the demo, right? To see how far away the computational complexity is treating us. Okay, so this is the code, right? And let's make, okay. So right now, I'm going to run that. So this is the case where we run different sizes. So the first we run is 1K by 1K by 1K, and then we run 2K by 2K by 2K. And let's see how much time it would take. So it takes a while to finish. Why? It shouldn't take that much time. Okay, here we go. Okay, oh, actually I ran more. Okay, so I ran several, right? First of all, I run 512, right? So for 512 by 512 by 512, it takes 0.13, right? So if we multiply that number by 8, how many? It's going to be 104, right? So that's about like 1 minute and 44 seconds. Sorry, 804. Sorry, how does that convert? Yeah, it's about like 1.04, right? So it's already not following this, right? It's supposed to just about 1 second, but right now this part is about 2 seconds, 1.8, right? But right now, if I want to scale up to 2K by 2K, if this is 1.8, as you guys said, it should be around 16, right? But right now, how much it takes? 22 seconds, right? So way more than you are expecting. And if you look at the CPI, the same instructions, right? It's the same instructions, right? I didn't change the code at all. I just changed the input size. But the CPI of the small matrix multiplication is only 0.68, which is pretty quick. With larger matrices, it's more than 1. With even larger matrices, it's closer to 2, right? The CPI changes as your data size changes, right? So a lot of you were thinking about, okay, if I run the same code, the CPI should always be the same. The answer is no. Like this case, even the data size change would change the CPI, right? But one thing that follows the complexity really well is actually your instruction count. 8 times more, 8 times more, right? So what does that mean is that, in fact, complexity only works for instruction count, but not for the execution time, right? And in fact, if you see the growth of CPI, you will learn that. So why is that? Why is that? So a lot of you can probably guess, okay, if nothing else, then it's probably cache misses, but be specific, what kind of cache misses? All right, let's take a look. Okay, so apparently we need some discussion. So why don't you guys go ahead and talk? All right, let's take a look. Okay, so after discussion, 41% versus 47%. So what do you guys think? So at least we all agree there is a factor of capacity misses. Why is that? Your memory footprint is huge. How big is that? You have 2K elements. Times A. 2K elements times A. How many? How many space do we need? 16K per row. 16K per column. That should be good.
Oh, well, BK, you're accessing it column wise. So, it'll be 2048 for BKJ times cache line is 8.
What kind of misses is that? Looks like we are good for one row. Looks like we are good for one column. Isn't that? Don't you agree with that? Yeah. Why is that?
I think it's in between loops.
In between loops? How do you run? How do you run this pieces of code?
So the column wise access wouldn't be need 32K for that single, because you need to access it column wise, right?
Okay.
So the first column you bring in 2K, and then for the next one you keep bringing your 2K blocks in the cache.
2K blocks?
Sorry, 2K, 16K blocks into the memory.
16K blocks?
Every time you would need to access element of the column.
Okay, so what kind of misses is that?
That is, so it would run out of memory, so its capacity.
Okay, so here's the thing, right? What's multiplication? We take a row and a column, right? So if you think about this, right? And then when in the next iteration, we take the same row, but a different column, right? However, right? Think about this. If we have 2K elements, each row would take 16K, right? That's quite a lot. You think each column would take also 16K. However, the answer is, like you said, right? Don't forget, every time when we take something in, it's not just the element itself, but also the block, right? So you are actually taking this whole block in, which is 8 times 16K. That's 64K. So what actually means is that before you come back to the same row, you already visited 64K, like 64K data. That's capacity miss, right? So the first type of misses that we would see is actually a majority of capacity misses, because each column would take 2K blocks, and each block has 8 elements, right? And each element is 8 bytes, right? So it's actually 2K times 64, right? That's more than your cache capacity. So you are going to see capacity misses, right? So how can we avoid that capacity miss? How can we avoid that capacity misses? Right? So if you remember what we have done in a previous profiling, if I can downsize my cache, my matrix, your CPI will go up significantly, right? So if we want to reduce the capacity misses, we need to reduce the size of matrix that we are multiplying each time. Agree? Right? How can we make that happen? How can we make that happen? So let's do a little bit of mathematical study. This is the definition of matrix multiplication. If I want to compute Cij, right, it's a sum of Aik multiplied Bkj from 0 to n, assuming the size of the k is n. We all agree with that, right? You can separate that by split it into 2 parts, right? So if you split it by half, then you will still get the same result, but you can have 2 separate loops of doing it, right? And each loop you are traversing on only half the amount of the elements in each row and column. So you can reduce the total capacity, or say the working set size of your code, right? You can further divide it into 4 different pieces, right? So that it's more likely to fit in your cache, right? Or you can divide even furthermore. So this is the property of matrix multiplication, that you can split your matrix multiplication into various size of tiles as you wish, various numbers as you wish. Right? So if you can break up multiplication and accumulations into something that always fit into the cache, then you can avoid all the capacity misses. So this is the theory behind matrix tiling, right? Since we can always partition this multiplication into different steps. So instead of going all the way down to the end of the row or all the way down to the end of the column, if I decided I want to split this matrix by half, then I can just go to half of the row, half of the column, right? So in this way, if this part won't consume the whole cache space, when I need to use this, it's more likely these blocks are also in the cache. So those are likely to be hit. And when I want to reuse the same row, it's still there. So it's going to be a hit, right? So by doing matrix tiling, right, I can potentially keep all the blocks that I need for multiplying this whole tile with the row together to eliminate all capacity misses, right? So that's the reason why we want to do matrix tiling, right? So for this example, if I do meshes tiling, I only need 10 blocks in this working set, which is significant reduction from the original use of cache, right? And the thing is that once you finish this part of the row, you don't need it for a while, right? So even though you have a cache that only can obtain 10 blocks, you are still fine because then you work on this, right? You don't need the priority one, right? The only cases that you would use them is when you want to perform this part, but that's a long time later, right? And at least for now, we don't have to worry about that, right? So in this way, sorry. Wait. Oh boy. Okay, in this way, once you do this partition, right? The good thing is that you are only going to see compulsory misses in performing this first tile multiply this first tile, right? And also, if you are working on this part, right, the lower half, you still have to multiply this tile. So if we do this first, right, this part, we only also see compulsory misses, right? So together with, we are actually bringing down our cache miss rate to only 1% at this moment, right? Now, if I want to work on this lower part, this part with this lower part, right? Well, I need more blocks. So this time I'm also going to see some compulsory misses again. But if I'm just multiplying this tile with this tile, the miss rate is still pretty low. However, you might be bearing the risk that the upper part will be kicked out, right? But again, if we want to reuse this part, then when we perform the rest of the computation, that will be pretty okay, right? So if you put this all together, this is the resulting code that you are going to write, right? First of all, the inner nested 3 levels of the for loop, they are performing each tile by tile multiplication. The outer nested 3 level of the for loop, they are picking the pairs of tiles that we want to multiply and put them in the right place. So this is why we see this 6 levels of for loop in play, right? So now, well, this example, right? If I have a tile that's only 8 by 8, right? I'm only going to use like 10 blocks, which makes my working set really small, right? However, for the Intel cache, it's like a 48 kilobytes of cache. We can accommodate 768 blocks, right? So if I just use 8 blocks, that utilization is pretty low. Don't you agree with that? Right? That utilization is really low. So what we are thinking is that, okay, we want to pick the right tile size, right? So that we can better utilize the cache. So what if today I pick the tile size to be 32? All right, let's take a look. Okay, so most of you picked the answer as C. Why don't you guys go ahead and talk to others? Why is it C? All right, so, well, I know most of you will pick that, but I want your solution to it. Why is it conflict misses? You just guess? Why is it conflict misses? Why? How do you know it's conflict misses?
Does it have to do with something with the tile size potentially? Since
Yeah, it has something to do with the tile size, but how do you know they are conflict misses?
since there's 6 variables, so when you allocate
Why do you have 6 variables? There's only,
6.
no, there are only 3 data structures that you are accessing, right? So to be honest, I wouldn't assume you guys come up with such an answer so quick. Because for this specific question, you really need to go through the process of cache emulation to know. So you have to list the addresses. And how to show that, we should talk about that in the next lecture. But before before you leave the classroom, don't forget, there is another reading quiz due next Tuesday, and next Thursday we have assignment 2 due. Other than that, enjoy the rest of the week. I will see you next week.